This video is the first introducing a very powerful group of techniques called resampling methods, which includes something called bootstrapping. So first we'll focus on the case using bootstrapping and these methods to estimate uncertainty, like confidence intervals, on a single parameter. So let's start with a motivating question like this one. What is the 95% confidence interval on this r squared value? We calculated r squared was 0.52, but what's the uncertainty? There isn't a standard calculation for this, but we can use a resampling method to get this information. They turn out to be extremely flexible and powerful techniques, and you can use them for really almost anything that you want to do. So you might remember that the definition of a confidence interval on the mean, so we'll step back from the r squared and talk about the mean first, because it's a simpler example and we can demonstrate how the method works. So basically, if you took many random samples from the population, 95% of those confidence intervals would include the true population mean mu. So I will illustrate how this works if we had a known population. So the curve on the left is our known population with a mean of 3. So if we can sort of simulate this method by saying, okay, well, let's take a random sample of 100 values from our population with a known mean and a known standard deviation. We'll calculate the mean of that sample, so the green dot is now a sample mean, which is an estimate of our original population mean. We can repeat that process many times, like 10,000 times or whatever, to generate something called a sampling distribution of means. So each of these green circles here now is a sample mean. So for each one, we've drawn 100 values, say, from our population and calculated that sample mean. So if we do that, say, 10,000 times, we get a distribution like this. This is a sampling distribution. It's not the original data. Instead, each point that makes up this histogram is a sample mean that we calculated from one random sample drawn from the population. And so given our definition of a confidence interval, it's just between the 2.5th percentile and the 97.5th percentile, the range that encompasses 95% of the sample means in our repeated trials. So I point out this is just one way of calculating these confidence intervals. It's called the equal tail method. It works best for symmetrical data. If you have a lot of skewed data, there are other methods that we're not going to talk about in this course. So that's fine. Okay, if we actually know the population parameters, but we never know them, right? We never know the population. We just have a sample. We have a single sample, something like this. So what can we do in this case? Well, it turns out that the sample is still the best information we have about the population. I mean, it happens to be the only information as well. And most samples, especially if they're big enough, do indeed closely resemble the population that they come from. So we can make some inference about the true population from this sample here. And essentially what we can do is we can resample this data with replacement. So sampling with replacement means that when we draw a value, we sort of put it back into the pool, we can draw it a second time. So we can resample a single observation more than once. And because some observations might be sampled twice or 3 times or even more, others may not be sampled at all. So this process of sampling with replacement extrapolates somewhat, at least, to the broader population. So it's a little bit more like our original model of drawing repeated samples from the population. And so this is a process called bootstrapping. This sampling with replacement is called bootstrapping. So we calculate the mean of that bootstrap sample, and we repeat this process many times to generate a bootstrap sampling distribution of the means. So you may be thinking this sounds like cheating. How can we get more out of our data than actually is there? We only have this sample. How can we extrapolate to the population? Does this even work? I guess the name bootstrapping kind of acknowledges that bit. It's from the saying, you pull oneself out by the bootstraps, which obviously you can't lift yourself off the ground just by holding on to your shoes. But it turns out that bootstrapping is really an okay thing to do. I'm not going to go into the theoretical justification. You can certainly read more on your own if you're interested. But just trust me that this is a technique that works, and it's not cheating. So the bootstrapped resampling distribution will look something like this. So this is basically taking 10,000 random samples from our single data set, but sampling with replacement. So just to compare, if you calculate the mean and the 95% confidence intervals using our parametric methods that you've used before, you get these values like 2.82 and 3.23 for the confidence interval. And it turns out that the 2.5th percentile and the 97.5th percentile of our bootstrapped resampling distribution gives you the same answer. It's not exactly the same because it's a random sample, but that's kind of beside the point. You can see that it's effectively the same thing. So this sort of demonstrates how the method works with something that we know, like the confidence interval on a mean, and you can use this same approach to calculate confidence intervals on things like the R-squared value that lack one of these standard formulas. So bootstrapping is resampling with replacement, so it maintains the data structure. We have the same number of observations or whatever, but it reshuffles the values to sort of extrapolate to the population. So as I mentioned before, each value can be sampled multiple times or not at all. The example on the previous slide is sort of trivial because we already had a formula for the confidence interval on a mean, and so we could just use that. But bootstrapping is useful in many other situations, like for non-normal data, when the mean and that confidence interval formula don't really apply. The really big benefit of bootstrapping is to estimate statistical parameters for things that have unknown properties, say like the results of principal components analysis, or PCA, which we'll discuss in a few weeks. Or we can use it to bootstrap estimates on things that don't even have a standard calculation, like R-squared in our example, or the coefficient of variation. So there is one caution, and that is to note that some parameters are inherently biased during this bootstrapping process. So measures of dispersion, like standard deviation or variance, are really the most common example of these biased parameters. So let's say that I resample this data on the left here with replacement, as our procedure for bootstrapping calls for. Remember that we can sample values multiple times or not at all if we're sampling with replacement. But the extreme values, the ones, say, near the edge of our data set, tend to be rare compared to values in the center, at least unless your data are bimodal, but for typical data which are relatively symmetrical and have a peak near the middle, the extreme values on the edges tend to be rare. And so that means that when we're doing our sampling with replacement, we're maybe more likely not to collect them than we would be to sample the ones in the center. So that means that we tend to underestimate the range of variability in the data, and the bootstrapped standard deviations are sort of systematically underestimated. And that's what you see on the right there. These are the sampling distributions of just regular bootstrap standard deviations, and that distribution, the histogram, if shifted a little bit to the left of the expected, so the value from our original data. And so because it's shifted a little bit to the left, the confidence interval will be shifted and offset a little bit as well. There are a variety of ways to correct for this, but we'll just cover sort of one fairly straightforward and simple one, and that's called the balanced bootstrap. And so the process just involves correcting the offset by adjusting each value. So each bootstrapped, say, standard deviation in this case, so for each one, we're going to add the difference between the observed value in our original data and the mean of all of our bootstrap data. So we're sort of adjusting each value and shifting it so that the mean of our bootstrap data is the same as the actual value in the original data, the observed value. So in the previous example, the mean bootstrap value is about 0.08 units smaller than the observed value from the original data, so we just add 0.08 to each of our individual bootstrap trials. We do 10,000 of them, so we add 0.08 to each of those 10,000, and that shifts the sampling distribution a little bit to the right, so now it's centered on the observed value, which you see in the balanced bootstrap on the right there.